Today we're going to be talking about probability distributions, so we're just going to start talking about them. All right. So far we've covered sampling methods as well as a little bit about just the basics and fundamentals of probability. In probability distributions, we're going to be putting those two ideas together and really working them so that we could get what we want out of them. And because of that, we need to talk about what sampling and probability cannot do. It can't tell us something, and because of that, we need probability distributions. And that's going to be the solution to what sampling and probability alone cannot accomplish. And within probability distributions, we're going to begin to talk about random variable and what that means and what the expected value is. Okay, so we now know a little bit about sampling, a little bit about probability. So in sampling, we know that what we are trying to do is estimate some variable by taking a sample from the population, right? So here is the population of all the people we're interested in, and we take a sample out, right? And we look at those individuals to try and estimate what that variable looks like in the population, right? We know a little bit about probability. Now, in a particular population, right? In a particular population, we know the chance of getting a specific sample. What is the probability of getting this particular sample, right? And you might want to ask yourself, well, what's the relationship between these two things? Well, sort of in one where we're getting a sample, we're actually getting a sample, and we're looking at the mean and the standard deviation of some particular variable in order to estimate that variable. But in probability, what we're doing is it's not that we're actually taking a sample. We're not actually taking a sample. We have a population, and we're trying to think about all the different kinds of samples, the sample space, and then calculate the probability of a very specific sample. Okay, so in one we're actually taking a sample, in the other we're not actually taking a sample. Here there are some limitations, though, because even if we try to take a random sample, right, one that is not biased in some way, even when we try to take a sample, we don't necessarily know how close that sample is to the population. Now here, we haven't taken a sample, but we know the probability of getting that particular sample, right? But we're still missing one little piece of the puzzle. Neither sampling nor probability helps us know the actual characteristics, things like the shape, middle, and spread of the population, right? So we could know how likely this sample is given a population. We could take a sample out and summarize that sample, right? But we don't know how to understand the population if we don't already know what it is. Right? That's a problem. So what do we do? Here is where probability distributions are going to come in. In probability distributions, what we're going to do is take this population and look at the distribution of all the different possible samples and get their probabilities for each sample, right? So this way, it's not that we're just calculating one probability for one particular sample, but we're calculating all the possible samples and all the probabilities that go along with it. And that's what's called a probability distribution. So we're no longer dealing with single probabilities or single samples, but we're looking at the universe of all the samples and the probabilities that go with them that might happen from a known population. Okay? Now, it doesn't necessarily have to be known as in, like, we definitely know that this is the population, but it could be a theorized population, right? Like a fair-headed, fair-sided coin or a fair dice, right? So, so those could be theoretical models, right? But that's what we call known population. We have some sense of the population, and from that we take out, we glean from it all the possible samples and all the probabilities that go with those samples. All right, so here's the big insight. Here's why we want to do that. First, we use probability, the fundamental principles of probability, to figure out what samples from known populations look like. We've looked at how to do it for one sample at a time. Now we're going to do it for all the possible samples, right? So we figure out what the distribution of samples looks like. Then we take a sample from a different unknown population, right? So here we have known population. And then we get all samples and corresponding probabilities of those samples, right? Then we have this unknown one, unknown population. And we take a sample. And what we do is we compare this sample to the results of the samples from the known population. Was this sample likely if this was our theorized population? Was this sample unlikely, right? In this universe of all possible samples from such a known population? And so if this sample is highly likely, given that we know that its probability, then we could say, maybe these two guys are similar, right? But if this sample is very unlikely, then maybe we could say, perhaps these two populations are not similar, right? So this one is different from this known population, right? So that's the insight. We're going to use these probability distributions in order to help us figure out samples that come from unknown populations to try and figure out what that unknown population is like. Okay, so it helps to sort of define what a probability distribution is. These are all the samples that can be drawn from a known population and their corresponding probabilities. Okay? So when you think about probability distributions, I also want you to think of what's called a sampling distribution. Because what it really is, it's not a distribution of single entities or people or companies, right? It's not a distribution of single data points. Instead, it is a sampling distribution. It is a distribution made up of a whole bunch of samples. Okay, so now that we know what probability distributions are for and why we need them so desperately, let's try to sort of smooth out the road from probability to probability distributions. Okay, so in probability, we learned about sample spaces. So remember, when we were talking about sample spaces, we're talking about all the different possible samples that you could have, right? So when we talked about flipping two coins, and we looked at, what's the probability of getting two heads in a row, right? We created these sample spaces of all the possible different outcomes, right? All possible outcomes, right? And so, for instance, if we looked at the sample space for two die, we might look at something like this. Die number 1 might be here, And die number 2 might be here. We might have 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. Sorry, it's a little small, right? And so if we looked at the sample space, that would be 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, right? Or it might be, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6, right? And you could fill in all the different possible outcomes, right? So there's 36 possible outcomes. And if you filled out the rest of this table, you could see the entire sample space. And each of these rules of the die, presuming that these die are fair, each of these would have a probability of 1 out of 36. So the likelihood of this out of all the possible outcomes, so out of 36, right? Now, that would be looking at the sample space. And that's the probability of all the different outcomes. But when we talk about a probability distribution, often we're talking about just one number and the distribution around that one variable, whatever that variable is. Here, notice that we have 2 numbers, right? But we may want something like the sum of 2 die, right? So here, the sum would be 2, and this sum would be 3, and this sum would be 4, right? And maybe we want a probability distribution that looks something like this. So here, I'll put all the different possible sums, right? I might not have room for this, so I might draw them a little bit separately. So for instance, can I have a sum of 0? No, I can't have a sum of 1 either, because if I roll 2 die, the lowest possible sum I could have is 2, a 1 and a 1, right? So I could have a sum of 2, a sum of 3, a sum of 4, 5, 6, 7, right? But I could also have, oops, I will continue this on this side because I ran out of room. I could also have sums of 8, 9, 10, 11, and 12. And I can't have any sums higher than 12 because that's the highest, so 6 and 6 on each die is the highest possible sum I could have, right? And my probability distribution would be, what is the probability of this sum, the sum of 2, right? Well, that would be only one outcome out of all 36 outcomes would give you that sum of 2, right? So that would be 1 out of 36. All right. And the same thing with 12, right? The only possible combination that could give me 12 is this 6 and 6 right there. So that would be also 1 out of 36, right? But now let's think about 3. How many rolls of the die could possibly be add up to 3, right? Well, 1 and 2, but also 2 and 1, right? Any numbers higher than that, and it's not going to work, right? And so here, we would write 2 over 36, because 2 different rolls could give us the same sum, right? So notice that not all the probabilities are equal, right? This one is less probable than this one. This is more probable. Okay, what about 4? Well, for 4, now we're starting to get into some bigger numbers here. So 1 and 3 will work, but so will 2 and 2, as well as 3 and 1, right? So that's going to be 3 out of 36. Notice a pattern here so far? 1, 2, 3. Also notice a pattern here. It's going to go like this, and like this. So let's continue that pattern and see if it's correct. So our prediction would be that the sum for 5 would be 4 out of 36. And let's see if that's true. So this sums to 5, and so does 4 and 1, right? But let's see if these diagonals also do. So these diagonals would be 2 and 3, as well as 3 and 2, right? And again, we know we could see our rule generalizing here. So that's going to be 4 out of 36, right? And actually, this ends up working all the way up to 7. So at 7, this is going to be the longest diagonal, right? So I'll fill that in right here. 6 and 1. Ooh. It looks a little messy, sorry. So 6 and 1, but also 5 and 2, but also 4 and 3, 3 and 4, and 2 and 5, and also 1 and 6, right? So all 6 of these here on the diagonal will add up to a sum of 7, right? And that's why in like games like craps and stuff, 7, that's like the highest probability roll. Settlers of Catan is another game where 7 is a high probability roll. That's why it's actually not allowed. That's why it's sort of not allowed. And here, you'll see that what happens after this diagonal is that it becomes smaller again, but in a perfectly symmetrical way, right? So what goes up, 1, 2, 3, 4, 5, 6, comes down, 5, 4, 3, 2. And that's because you're just finding those diagonals, but now it's going from big to smaller and smaller and smaller, right? Until you end up here with 1 out of 36, right? So this is a common probability distribution for us to start with because it's really easy for us to see how we got these probabilities from these sums. So this is a relatively small sample space, and it's a relatively small probability distribution we could deal with. There are going to be bigger spaces, ones that we cannot necessarily calculate by looking at all the different combinations, and we'll look at some of the algorithms and theorems that have been developed in order that we could have these shortcuts so that we don't have to look at the entire sample space. But I want you to know where this comes from. It all comes from the sample space and looking at it in terms of their respective probabilities. Okay.